Alright guys, good morning, good afternoon, good evening, good whatever it is for you today. We're going to be taking a look at a proof for the double angle identities for a trig function sine and cosine. This proof was pointed out to me by one of my classmates. It's a very elegant proof, very simple proof. You may find that you pick up on what I'm doing pretty quickly because it is so simple and elegant. So we're just going to start off with the old famous Euler's formula. E to the power of theta I is equivalent to cosine of theta plus I sine of theta. So we're going to be utilizing this for our proof. So now I want you to imagine, since we're talking about double angle, what if we make the angle twice theta? So E to the 2 theta I. Based off of the properties of exponents, we can say that this is also equal to E to the theta I quantity squared. Because if you have a power to a power, that's the same thing as multiplying the two powers as one power. That was pretty poor wording, but you can see what I'm talking about here. So we're going to expand out both sides of this equation. So E to the 2 theta I, we can come over here, and let's just substitute in 2 theta. So cosine of 2 theta plus I sine of 2 theta. That makes sense? We should just take that as the angle. Now over here on the right, let's do the inside portion first. So e to the theta I, as we've shown earlier, is cosine of theta plus I times the sine of theta. But again, we're squaring all of that. So left side is going to stay the same, but we're going to expand the square on the right side. So we have cosine of squared theta plus 2I cosine theta sine theta plus minus sine squared theta. As my error has pointed out, we need to be careful that this is indeed a minus. And that is because we have I sine theta multiplied by I sine theta, and I times I yields -1. So that's why we have the minus sign in front there. So now we have these two sides of the equation, and here's what we're going to do. I'm going to take the real part of both sides of this equation. So the real part of cosine 2 theta plus I sine 2 theta should be equivalent to the real part of cosine squared theta plus 2I cosine theta sine theta minus sine squared theta. So the real part of this is just going to be this component because this part over here has an I, so cosine of 2 theta. That's going to equivalent to the real part over here. This part doesn't have an I, this part doesn't have an I, the middle part does, so we can discard that. So cosine squared theta minus sine squared theta. And that is the first of our double angle identities. Cosine of 2 theta is equivalent to cosine squared theta minus sine squared theta. This is indeed the identity for double cosine. Similarly, we can take the imaginary part of both sides of the equation. So the imaginary part of cosine of 2 theta plus I sine of 2 theta is equivalent to the imaginary part of cosine 2 theta plus 2I cosine theta sine theta minus sine squared theta. And as you've probably already guessed, this is the imaginary part here, sine of 2 theta. And over here, this is the imaginary part, 2 cosine theta sine theta. And that is the other double angle identity. So there you go. That is a simple and elegant proof the double angle identities using Euler's formula. I quite like this, and I think it's actually an easy way to remember the identities. So yeah, imaginary numbers, they work. I hope you guys enjoyed this video. If you have any questions or want to see a video on a particular topic, just let me know in the comments down below. Thank you for watching and have a great day.